Today we have Dr. Manuel Scherf from the Austrian Academy of Sciences in Graz, Austria. So I'll briefly introduce him. So he finished actually his master thesis from University of Graz on the topic of effect of supernovae on the Earth's climate. And then he moved to the Space Research Institute where he actively worked on international research infrastructure projects like Europlanet. And then he started a PhD, back to science and University of Graz. And he finished it on the topic of the influence of sun and host stars on atmospheric evolution and the habitability of terrestrial planets. Since then, he is working as a postdoc, and he'll talk about some of his recent work on Earth-like habitats. So the floor is yours, Manuel.
Thank you very much for the introduction. So as Kaustup said, I'm Manuel from the Space Research Institute in Graz in Austria. And I'm mostly working on atmospheric evolution, on planet-star interaction, and what that actually means for planetary habitability. And I'm mostly interested in Earth-like planetary habitability. And today I want to talk a little bit about the evolution, emergence, and prevalence of Earth-like, so-called Earth-like habitats in the galaxy. I will soon discuss a little bit more what I actually mean with Earth-like habitats. But what I can already say is that this yellow band that you see here, this Earth-like atmosphere at Earth, the pale blue dot, as Carl Sagan coined it more than 40 years ago, is very important. It is basically key if you want to understand Earth-like habitability in the galaxy and beyond. And first of all, I want to talk a little bit about what actually we mean about Earth-like habitats, about toxicity limits for complex aerobic life, and what we actually understand as complex aerobic life. So first of all, well, Earth-like habitats is defined very easily, very simple. So it's a rocky planet in the habitable zone for complex life. I will soon explain in more detail what I mean with habitable zone for complex life. That have an N2O2 dominated atmosphere with minor amounts of CO2, so with less than 10% mixing ratio CO2, which is very important, as you will see. And those N2O2 dominated atmospheres with little amounts of CO2 are actually biosignatures. Basically, there are many studies on that, so you cannot have nitrogen and oxygen in the atmosphere in high amounts. Our geological timescales stable, basically. So if you would find one of those atmospheres, that would be a strong sign that there would be some kind of Earth-like life there. What do we actually mean by complex life? We understand as complex life, and that's a quite narrow definition, some kind of millimeter to meter sized oxygen-breathing animals with a blood circulatory system. And the blood circulatory system actually is quite interesting and quite important. You can actually define toxicity and physical limits of atmospheric partial pressures for CO2, for O2, and for N2, and I want to start with O2. And that's actually hard physical limits if you want to have this kind of complex life being present on a planet. So oxygen is the best energy donor for life. So you won't find an element that gives more energy to life than oxygen. So if you really will have complex life, it will most likely breathe oxygen. And there is one interesting thing with oxygen. So if you rely on oxygen as your energy donor, you can either do that via diffusion through your body or via some circulatory system. The problem with diffusion is that you need quite a lot of oxygen in the atmosphere that you can diffuse the oxygen to your entire body, that the most inner part of your body really gets some oxygen. You need some certain partial pressure. And if you want to, so for a centimeter, for instance, you need about 100 millibars of oxygen, at least in the atmosphere, that you can diffuse oxygen through the entire body. That's the reason why insects, for instance, do not grow bigger than about a centimeter or a little bit more in our present-day atmosphere, in height or in diameter, because otherwise they couldn't diffuse the oxygen through their entire body, and they could not give the energy to the body that they need. So if you want to grow bigger, you want to invent some kind of a circulatory system to get the oxygen to your entire body. But to do that, you need some minimum partial pressure in the atmosphere, because if your body is too little, you cannot have a circulatory system, because you have some physical limits, like adhesion, for instance, that that doesn't allow a proper circulatory system. So you have to grow the size of a millimeter, a few millimeters, or a centimeter. And to do that, you need about 100 millibars of oxygen in the air. So you can only get bigger animals or complex aerobic life if you really have something like 100 millimeters or more of oxygen in the atmosphere. So that's some kind of a hard lower limit for complex life. And there is also an upper limit for oxygen in the atmosphere, which is also some kind of a physical limit. So if you go to partial pressures for the oxygen that is around 300 millibars, you will reach the flammability limit. So your organic matter on your planet will suddenly start to uncontrollably burn. And during the Ordovician, that's about 320 million years ago, we had about 300 millibars of oxygen in the air. And there are indicators that there really were large-scale fires on the planet. So if you really get more oxygen into the air, your planet will start to regulate it down again, and you will end up with something like 300 millibars or lower. And also in the Ordovician, insects indeed grew much bigger because there was more oxygen in the air, and the diffusion of oxygen into the body was more efficient. For CO2 and N2, you can define some toxicity limits. I know that might be different on other planets because we do not know what evolution does on other planets. But it's a good first step to check for which atmospheres you should actually look like if you want to search for complex animal-like life. So for N2, for instance, if you go to something like 2 bars in the atmosphere, it will become toxic for any animal that we know. So there are several studies on that. More important is CO2, however. So if you go to something like 100 millibars of CO2 in an atmosphere, which is about 10% mixing ratio CO2 if you have a 1 bar atmosphere, it will be toxic for any animal life on Earth, and it will not survive it. Young animals even won't survive much lower CO2 partial pressures, actually. So you have some kind of an upper limit of 100 millibars of CO2 in the atmosphere. So in total, and well, you can also define some lower values. So if you go to very low CO2 partial pressures, at some point photosynthesis will stop. That's probably the fate of the Earth. So in a few 100 million years, CO2 will be drawn down so much that photosynthesis cannot happen on the planet. And that will also be the end of complex life. So all in all, you will have an atmosphere that can maybe have up to 2 bars, if you really look at N2, O2 atmospheres, with a few 100 millibars of O2 and with little CO2 in it. So we want to search for that. And CO2, however, is important also in other respects. But first of all, I want to come to this habitable zone for complex life. So you probably all are familiar with the concept of the habitable zone. So if you're in the habitable zone, liquid water is liquid on the surface of the planet. If you go further outside, your water will freeze. If you're inside the habitable zone, your water will evaporate. And Schwieterman et al. 2019 were the first who introduced the concept of the habitable zone for complex life, where they basically assumed that the outer part of the habitable zone is restricted by a maximum of, let's say, 100 millibars of CO2 in the atmosphere. And because if you go further out in the conventional habitable zone, you need a lot of CO2 in the atmosphere that, to heat up the planet, that the water on the surface can indeed be liquid. If you restrict yourself, however, to only 100 millibars of CO2 in the atmosphere, your habitable zone will shrink to about 30% of its conventional size. And that also means that you will have much less rocky planets within this habitable zone for complex life than you will have in the conventional habitable zone. And with that, you will also have less planets in the galaxy, for instance, that can indeed host complex life as we know it. Then there is another thing with CO2, and that relates to thermal stability, which I will show you soon. But first of all, I just want to briefly show you why N2, O2 atmospheres are actually biosignatures. So you see here simulations from a paper that we published with a PhD student in 2021 who developed a box model of the Earth's early atmosphere. So until about the great oxygenation event, and who included atmospheric sinks and sources for nitrogen in the atmosphere. So you have certain sinks, which is, for instance, biological nitrogen fixation, which is microbes that convert N2 into NH3. You have high energetic events like lightning, cosmic rays, and meteorites that actually fix N2 also in NHX or into NOx, depending on the atmospheric composition. You have atmospheric sources like biological denitrification, which can convert NOx back into N2. biological analogs, which can convert NHX back into N2, which are both processes that are performed by microbes that evolved some 2.6 billion years ago. And you of course, have volcanism as a source. You have some disputed other sources, like iron can convert NHX and NOx, probably 2 into N2, and you probably also have rock weathering that brings N2 back into the atmosphere. But what happens if you model all that together? So the dotted line that you see here is a lifeless world. We always start with 0 nitrogen partial pressure. It doesn't matter so much if you start with an atmosphere, with a bar or something like that, it will have a similar outcome in the end. So if you have a lifeless world, your nitrogen will increase because of volcanic degassing, which basically outcompetes the abiotic sinks, like lightning, cosmic rays, and meteorites. If you would have some kind of a great oxygenation event, which is unlikely in a lifeless world, suddenly your nitrogen would be drawn down because your abiotic sinks, in particular lightning, become much more effective since the N2 reacts with the oxygen and will just drawn out of the atmosphere. If you include biological nitrogen fixation in it, which started on Earth about 3.5 to 3.8 billion years ago, you will see that you do not build up any nitrogen basically at all. However, if you also include other sources like this iron-induced nitrogen outgassing, which, as I said, is disputed, and specifically anamox and denitrification as biological sources, your nitrogen will increase first due to this iron conversion of NHX. Then when biological nitrogen fixation starts, it will be drawn down, but suddenly, as denitrification and anamox starts, you will have a huge rise in nitrogen in the atmosphere, and also at that great oxygenation event, you will start to have a rise in nitrogen because this denitrification and anamox processes will become more efficient. And there are other studies as well that come to a similar conclusion. So if you find something like nitrogen, oxygen atmospheres, it's very likely a biosignature for Earth-like life. But now, I want to come back to the upper atmosphere, which we are mostly interested in, and why CO2 matters a lot. So here you see a sketch of an Earth-like atmosphere. So a nitrogen-oxygen dominated atmosphere with little CO2. And you see temperature on the x-axis, altitude on the y-axis. Starting from the surface, you have the lower atmosphere going up to about the mesobaus or the homobaus, so where it is well mixed. We ignore that for the moment and just are interested in the upper atmosphere, so basically in the thermosphere, which goes up to the exobase, which is the part in the atmosphere where the atmosphere becomes collisionless. So we define that as the end of the upper atmosphere, basically. So the thermosphere describes the upper atmosphere. And you see that in the thermosphere, suddenly the temperature is rising significantly for Earth-like atmospheres. So the temperature goes up from about 200 Kelvin at the mesobaus to up to 1,000 Kelvin at the exobase. And it also expands up to 500 to 1,000 kilometers, depending on the condition. And the reason for that is that the short wavelength radiation of the sun, or of any star for that matter, which is the X-ray and extreme ultraviolet radiation below about 100 nanometers, is absorbed in the upper atmosphere. That's why it is called thermosphere, actually. So this part of the atmosphere is quite dilute, but this short wavelength radiation is absorbed there. And nitrogen just absorbs it, but doesn't really re-emit it, so it heats up and the atmosphere expands. So you would need some kind of coolants in the upper atmosphere to keep the atmosphere from expanding that much. So basically, if you want to study upper atmosphere structure, the important things are the mass of a planet, as you will see soon, the distance to the host star, the incident radiation and particle flux, a little bit the surface temperature, and atmospheric composition, because atmospheric composition matters a lot. If you take a look at the planets in the solar system, here again, temperature profiles of the upper atmosphere, temperature on the x-axis, altitude on the y-axis. You have Mars, you have Venus, and you have the Earth. So the solid lines in this case. And Mars and Venus have CO2 atmospheres. And CO2 is a very efficient infrared coolant. So it absorbs the short wavelength radiation, re-emits it in infrared. This is a problem in the lower atmosphere, as you may know, because that's the reason why we have our current climate change, because the infrared radiation that the CO2 emits cannot be re-emitted into space, but it's just reabsorbed in the lower atmosphere and heats the lower atmosphere. But in the upper atmosphere, it absorbs the short wavelength radiation, it re-emits it in the infrared, and since the upper atmosphere is so dilute, most of it will just be emitted into space. So that's effectively cooling the upper atmosphere. And you see for Mars and for Venus, the upper atmosphere ends around 200 kilometers above the surface, and the temperature is around 200 Kelvin. And that, even though Mars is 10 times less massive than the Earth, and Venus has a surface temperature of about 700 Kelvin due to the CO2. But still, the upper atmosphere is very compact and very cold. For Earth, you see the difference. It's a nitrogen-dominated atmosphere, and it's very hot and can reach, depending on conditions, even up to 1,000 kilometers. If you would put Mars to Earth's orbit with the same atmosphere, well, the temperature would rise a bit, the exobase would also rise a bit, but still it's rather compact. If you would give Venus an Earth-like atmosphere, you see what happens. So Venus receives about twice the XUV flux than the Earth, and the upper atmosphere will start to heat up significantly and would also rise a lot, expand a lot. So you see that composition really matters. And if you want to have a stable atmosphere, a compact atmosphere, you need infrared coolants in the atmosphere. The best one, or one of the best of those, is CO2. But what happens now if you take an Earth-like atmosphere and radiate it with higher XUV fluxes? So this figure is adopted from a paper from Janet Au 2008, who ran sophisticated upper atmosphere models. And you again see the temperature on the x-axis, the altitude on the y-axis. You again have an N2O2 dominated atmosphere, this time with just 400 ppm CO2, so our present-day atmosphere. And again, there you have the exobase levels, and the numbers here basically just mean the XUV flux or EUV flux as a function of present-day flux. So this is the present-day atmosphere. This is the present-day atmosphere radiated with 1.5 times the present-day XUV flux on its top. And you see that the more you irradiate it, the more it will expand. And around 5 to 6 times the present-day flux, something interesting happens. Suddenly you get a peak in the temperature in the thermosphere. And when this starts to happen, your atmosphere starts to adiabatically expand and basically just escapes into space almost immediately. So a 1 bar atmosphere you can lose if you are in that regime within 1 million years, which is geologically speaking almost nothing. And you see for 20 times the present-day EUV flux, if this atmosphere would somehow remain to exist, the exobase would be around 100,000 kilometers above the surface, which is even above the present-day magnetopause range. So clearly those atmospheres are not stable and will be lost almost immediately into space. For Mars, it looks a little bit different, or for CO2 atmospheres in general. So that's simulations with the same model by Janet Au 2009. This time you have the CO2 atmosphere of Mars. And you see, if you compare the y-axis, the atmosphere remains relatively compact, but still for 20 times the present-day XUV flux, it reaches about 10,000 kilometers, which is about 3 Martian radii. And here also something interesting is happening. So around that point, the CO2 in the upper atmosphere will dissociate because the flux is just too strong. It heats up and it again gets lost very quickly into space. And it doesn't matter whether you have just a few millibars bar or 3 bars in your atmosphere, it always looks almost the same. And also here you lose the atmosphere very, very fast. So if those planets or if those atmospheres are irradiated with these high XUV fluxes, they will just lose the atmosphere. The atmosphere cannot be stable thermally. And that's actually not such a high XUV flux as you will see. So how does that change if you make some kind of a mixing between N2 and CO2? So that's what we looked at in a study in 2021 with our own upper atmosphere model. And this time you see just the exobase altitude, so the top of the upper atmosphere, which are those different lines, as a function of different N2 CO2 mixing ratios and as a function of a present-day XUV flux, basically. So for a nitrogen-dominated atmosphere with 1% CO2, you see that basically the same happens as in this case. So where you see if you are around 5 to 6 times the present-day flux, your atmosphere starts to expand and will escape. For 1% CO2, something similar happens around 6 times the present-day flux. Your exobase level goes up and the atmosphere will also escape into space. If you go to 10% CO2, the atmosphere remains stable for longer, of course. So somewhere between 8 and 10 times the present-day XUV flux, you still will have the strong expansion of your atmosphere, and it will again escape into space. And be reminded, those 10% CO2 within a 1 bar atmosphere are 100 millibars of CO2, so that's about the toxicity limit for animal-like life. So if you go to higher CO2 mixing ratios, Earth-like complex life will not be able to survive those mixing ratios. But of course, the higher you make the mixing ratio of CO2 in your atmosphere, the longer it remains stable. However, even 100% CO2 mixing ratio, if you go to this 20 times, maybe 25 times the present day flux, will at some point not be stable anymore and escape into space. You can take this data and check what CO2 mixing ratio you would actually, first of all, how does that relate to solar or stellar evolution? So here you see two plots from Du et al. 2015, who investigated how rotation rate evolution of solar-like stars correlate with XUV flux evolution. And on the left, you see the rotation rate evolution of solar-like stars as observed within several galactic stellar clusters. And at the beginning of the lifetime of a star, you have a very divergent distribution of stellar rotation rates. So you have slow rotators all the way up to fast rotators. And usually you pick out those three tracks, which are basically just the 5th percentile, the 95th percentile, and the 50th percentile of the rotational distribution of solar-like stars at the beginning of their life. So that's the slow rotator, moderate rotator, and the fast rotator. And you see that those rotational evolutionary tracks converge after about 1 billion years. That means that all solar-like stars probably start initially with a different rotation rate, but end up after 1 billion years with about the same rotation rate. So just from that, we cannot know whether the sun was initially a fast rotator, a slow rotator, or something in between. But the interesting thing is that those rotation rates correlate with the XV flux evolution. So at the beginning, all of those different rotators are saturated in the XUV. When they reach the main sequence, however, those tracks diverge, and you see that the slow rotator has a much lower XUV flux than the fast rotator by more than an order of magnitude during the first 1 billion years. And then they again converge. And here is the present-day sun, and all of those XUV flux tracks basically here scaled to the present-day sun. So here it was assumed by Du et al. That all solar-like stars will reach the XUV flux of the present-day sun at 4.5 billion years. And here you see also the activity level of the present-day sun. A more recent study by Johnston et al. 2021 investigated the same thing, but not only for the solar-like stars, but for the entire stellar mass range below 1.25 solar masses. But here you see again solar-like stars. Again, here the X-ray luminosity on the y-axis, so that's basically the same as here, the X-ray luminosity. And on this y-axis, I'm showing you the X-ray flux in the middle of the habitable zone. And if the star has a planet in the habitable zone with a 10% CO2 atmosphere, with the rest being nitrogen and oxygen, or nitrogen alone, if your star is above this line, the X-ray or XUV flux in the habitable zone is too strong that the atmosphere would be stable. If the star would be below the nitrogen-dominated atmosphere with 10% CO2 would be stable. Here it would be not stable. Here it would be stable. And you see that for slow to fast rotators, it takes about 1 billion to maybe 2 billion years that such an atmosphere is stable in the habitable zone of a solar-like star. And an interesting thing here on this study is this study did not scale the XUV flux or X-ray flux to the present-day sun, but just took the average value of a solar-like star, and they found, in agreement with some other studies, that the sun actually is anomalously weakly active. So the average solar-like star is more active than the sun at 4.5 billion years. And that's an interesting coincidence. If you take now this study and compare it with the rotational evolution of a solar-like star of the sun, you can investigate what was the minimum mixing ratio that was needed in the Archean Earth's atmosphere, that the atmosphere was stable. And we find something like that. So that's slow rotator, moderate, and fast rotator again. And you see from 2.5 billion years ago to 4 billion years ago, so during the Archean, what was the minimum CO2 mixing ratio in Earth's atmosphere that the atmosphere would have been thermally stable compared to the axial reflux evolution of the Sun for a slow, moderate, and fast rotator. And you see for a slow rotator, 4.0 billion years ago, you needed about 40% of CO2 in the atmosphere for the Earth's atmosphere to be stable. So if the CO2 mixing ratio was lower, Earth would not have been able to have an atmosphere 4 billion years ago. And you also see that moderate and fast rotators were not possible for the Sun, because otherwise the Earth would not have had an atmosphere prior to 3.5 billion years ago, which is relatively unlikely. So that's a strong indication that the Sun was a slow rotator. And it also means that more active stars, the planets around more active stars cannot have an atmosphere when the axial reflux is too high. And you can also see that for Mars, for instance, I do not go into very much detail of this plot, but you basically just see sources and sinks for the Martian atmosphere. The most important sink is the thermal escape due to the axial reflux, which is this blue line. That's basically cumulative CO2 pressure that you can lose from the Martian atmosphere within the first 600 million years due to the axial reflux of the Sun, assuming that the Sun was a slow rotator. And you see that you can lose for the first 500 to 600 million years about 200 bars of CO2 from Mars. So if Mars would have been quite oxidized early on, if it would have outgassed all its CO2, so that's a very optimistic scenario where Mars would have had an initial CO2 budget of 120 bars, you see that all of this CO2 would have been lost within about 100 million years. And then there would have been no volatiles left to outgas an atmosphere later on. If you assume that Mars would have been probably more reduced at the beginning, if it only outgassed a bit of CO2 or CO and outgassed most of it later on, when thermal escape started to diminish because of the decrease in axial reflux of the Sun, you see that Mars could have built up an atmosphere after about 500 to 600 million years, so about 4 billion years ago. It could then have lost it via other atmospheric escape processes like interactions with the solar wind. So it indeed could have had an atmosphere about 4 to 3.5 billion years ago that was about a bar in density. That's exactly the time on Mars where we also see that there was liquid water present on the surface. If the Sun would have been a moderate or a fast rotator, this would not be possible, and Mars could not have had an atmosphere at all. So what can we learn now from the stability of Earth-like atmospheres on the existence of Earth-like habitats in the galaxy? So now I'm going from the solar system to the galaxy and talk a little bit about how much of those Earth-like habitats may exist in the galaxy. And before I go back to atmosphere, I want to talk a little bit about the galactic habitable zone, which you may know. So the galactic habitable zone often includes is this area in the galaxy where life or complex life can actually evolve, and it most often includes the radiation environment, which is mostly lethal effects by supernovae or gamma ray bursts. So if a supernova explodes close to a stellar system, it will receive a very high energy radiation, and you will probably sterilize your planet. Stellar metallicity is an important factor, because if your metallicity is too low, you cannot form rocky exoplanets. You could also take into account the long-term dynamical stability of a system due to close stellar encounters, which is often not included, and which is almost never included are things like the galactic evolution of aluminum-26, of other elements like the radioactive elements that you need for the thermal evolution of a planet, and other mineral ratios that change over galactic history. But here we take into account the radiation environment of supernova and metallicity. And I want to show you here those black lines basically from the model of Gowin-Lockett et al. That's basically the probability to not being sterilized by supernovae as a function of distance from the galactic center. So here is the galactic center. That's the distance in parsec. That's the probability that your stellar system is not sterilized by supernova. And you see that the probability is very low towards the center where there are more supernovae, and the probability that you are not sterilized is very high towards the outskirts. I will soon tell you a little bit more about that. But first of all, I want to talk a little bit about metallicity. So here you see a plot from Johnson and Lee 2012, which shows all the discovered exoplanets at that time. and here is distance from the star, and here is stellar metallicity. So 0 is the solar value. And you see that basically most of the planets are above minus 0.5. All of the planets that are below are basically gas giants. And that picture didn't change until the present day. So all of the rocky exoplanets that we discover are basically somewhere above minus 0.5. So if the metallicity of a star is lower, you cannot form rocky exoplanets. And you have to take into account that if you want to make a model of the galaxy and where you could have a rocky exoplanets existing, where you could have habitable planets. For this, you also have to take into account the metallicity distribution in the galactic disk. So here you see from Hayden et al. 2015 the metallicity distribution in the galactic disk. Again, here is the galactic center. That's the distance from the galactic center. That's the height from the galactic ecliptic. And you see that metallicity is increasing towards the center on average, and it's increasing also towards the galactic midplane. If you take a look at the evolution of metallicity in the galaxy, in the outer disk, which is to about 8 kiloparsec, and in the inner disk, which is inside 8 kiloparsec, you see that metallicity rose significantly over the history of the galaxy, meaning that old stars will, on average, have a lower metallicity than the newly formed stars. And stars closer to the galactic center will also have a higher metallicity than stars that forms further outside. That's what you basically see in those other plots here from other studies that include supernovae and metallicity, and you see that the probability that you could have a habitable planet is very low farther out in the galaxy because there the metallicity is low, and the probability to have a habitable planet is also very low towards the inner parts of the galaxy because the supernova explosions are so high. And somewhere around the sun, most of those models find that the probability to have a habitable planet is the highest. Now you can take a model of the galaxy like the one from Macmillan 2017. So again, the galactic disk, galactic center is again here. And here you see all of the stars in the galactic disk, which is around 100 billion. The exact number is not so important. And you see that most of the stars are towards the galactic center. If you include the effects of supernovae on this stellar distribution, you will see that most of your stars towards the galactic center are kicked out. So suddenly you have a peak somewhere inside the orbit of the sun, which is around 8 kiloparsec. You can take this distribution and display it differently. So that's the same distribution, but this time it's on the x-axis you see the birth age of the presently existing stars within this sample. And here you see stellar mass. So you see that most of the stars presently existing in the galaxy that are within galactic habitable environments are very old and low mass M dwarfs. If, however, you also include the effect of metallicity evolution onto this sample, you will see that most of those old low mass stars are kicked out because they're very old, the metallicity is very low, and you see that the sample gets homogenized. However, it's still dominated by low mass stars. But nevertheless, if you just include this galactic habitable zone concepts, you will find that maybe 10 to 20% of your stars may provide habitable conditions. Now I want to go back to atmospheric stability and to stellar evolution. So this plot you have already seen. It's basically, again, for solar-like stars, the plot as you've seen before, the XUV flux in the habitable zone, the threshold for a nitrogen-dominated atmosphere for 10% CO2, and the threshold for a nitrogen-dominated atmosphere for 1% CO2. And you see, as I already said, for a solar-like star, it takes about 1 billion to 2 billion years that the star crosses the threshold. But how does it look like if you go to lower mass stars? So if you go to a star that has about 75% of a solar mass star, you see that the star remains active for longer, and it crosses those thresholds later. So for the 10% CO2 case, it takes about 2 to 3 billion years that a star with 75% solar masses allows for the stable existence of an Earth-like atmosphere. If you go to 50% of a solar mass star, it takes even longer. It takes about the lifetime of the present-day sun already that you can have a stable Earth-like atmosphere. Or with 1% CO2, it may never be stable. If you go really down to the low mass M dwarfs, it basically takes forever. So it may take longer than the present age of the universe that those stars decrease in activity to such an extent that an Earth-like atmosphere could be stable. And for example TRAPPIST-1, which is 8 billion years old and has a mass of about 0.08 solar masses. Its XUV flux is somewhere here. So it has still about 100 times the present-day XUV flux that we have presently here on in Earth's orbit. So an Earth-like atmosphere will not be stable on the TRAPPIST-1 planets. And that's in agreement with the JWST observations, at least for now. So you can now take this stellar evolution model from Johnson 2021 and apply it onto our galactic distribution of potentially habitable stellar systems and see on which of those stars Earth-like atmospheres could probably be stable. And then something like that comes out. So for the 10% CO2 mixing ratio case and for the 1% CO2 mixing ratio case. So you see that basically all young stars and all low mass old stars are kicked out of the sample because here nitrogen-dominated atmospheres with 10% CO2 cannot be stable in the habitable zone. For 1% CO2, more of those stars are kicked out because the atmospheres are less thermally stable. And you see the sun always is, of course, within the sample because we have a stable Earth-like atmosphere. There's another problem, geologically speaking. So if you go to ages that are older than 6 billion years for planets that have the same radioactive heat budget than the Earth, those planets will start to become geologically inactive. So if your planet is located somewhere here, it will not be able to outgas actually an Earth-like atmosphere. So those planets will basically be dead and not be valid for complex life as well. But if you just take into account this XUV stuff and the galactic habitable zone, you will find that maybe, well, 1% of all stars in the galaxy will be able to host Earth-like habitats, so planets with Earth-like atmospheres, depending on the parameters and on the exact CO2 mixing ratio. And that's a maximum number because this evaluation doesn't include many other effects like non-thermal escape via interaction of this stellar plasma environment with the atmosphere, the effect of flares, UV habitability, and other stuff. So the actual number of stars that can host Earth-like habitats is pretty low. Then you could also, of course, there's another problem, then not all of those stars will have planets, for instance. So there is this famous eta-Earth value, which is the number of, or the occurrence rate of rocky exoplanets within the habitable zones of solar-like stars. And that value is not very good established. So just over the last 5 years, this value is ranging somewhere between 1% of all stars and 30% of all stars. But the newer studies, and you see here several different studies from the literature, that the black dots with the arrow bars are the eta-Earth values, so the occurrence rates of rocky exoplanets in the habitable zone, and you see how it is varying. But during the last years, studies more tend towards the smaller value on average, basically. And if you want to take into account the habitable zone of complex life, of course, you have to scale that to the smaller habitable zone of complex life, meaning that this occurrence rate will shrink even further. You could also implement some kind of appropriate amount of water on the planet. So complex life needs water, and you most likely will need continents, so surface, land, and ocean on your planet. And not many of the planets will evolve subaerial land and ocean at the same time, because you will most often end up with some kind of a dichotomy that you have either an ocean planet or a desert planet. You could also think that the large moon probably was important. Here we also know from modeling that large moons are relatively rare. The obliquity argument, so that the large moon stabilizes the axis of the Earth, which was often argued for the moon to be important, is wrong. So we know nowadays from studies that the Earth's axis can also be stabilized without the moon, or that large moons can even tend to destabilize an axis. But there are several other interesting arguments that favor the existence of a large moon. Like we need the moon, for instance, for nutrient upwelling in the oceans. So if you wouldn't have the moon, all the nutrients or dead organisms would just sink to the ocean and would just be gone from the nutrient cycle, which would be very bad for the biosphere. So if you just implement those 3 parameters within its large arrow bars, you find such a distribution of planets around stars of certain stellar masses. And the solid lines are for 10% CO2, the dotted lines for 1% CO2, And no matter which parameters you take, you always find that it is most likely that you find planets with Earth-like atmosphere somewhere around 0.8 solar masses, so somewhere in the K-type star regime. So we mostly search around M-dwarfs because it's easy. We try to find some around G-dwarfs, which is almost impossible. We should look more closely to K-stars. There you will most likely find most of those Earth-like planets, and that's also in agreement with 2 or 3 other studies that did something similar. And still, you will find very little of them. So you may find in the galaxy, well, a few thousand or maybe a few 100,000 of those planets, and that's still a maximum. Because many other factors are not included, of course. For instance, if you take stellar parameters, you need the right UV environment that you can have prebiotic chemistry. And just on this figure by Spinelli et al. 2023, you see the UV habitable zone, so the UV flux that you need that you can actually kickstart prebiotic chemistry, and the normal habitable zone, and you see that those only overlap somewhere in the K-dwarf to G-type, spectral type regime. And of course, as I already said, the question is, are binary stars habitable? You have to account for the stellar plasma environment, stellar flares. There is also something like a photosynthesis habitable zone, and all of them must overlap. Of course, you have many other planetary parameters. You may create a hydrogen-dominated atmosphere. So if Earth would have grown to 1 Earth mass within the Solar Nebula, for instance, we would have ended up with a thick hydrogen atmosphere, and the Earth would not be habitable. You need carbon silicate nitrogen cycles on your planets, for instance. You need the right radioactive heat budget. You need still CO2, N2, and O2 at your planet after the highly active phase of your star. You probably need an intrinsic magnetic field. You need the origin of life. You need the origin of photosynthesis to indeed involve such an atmosphere. So the actual number of Earth-like habitats in our galaxy might be pretty low. And yeah, with that, I think I leave you with my conclusions. Thank you very much. And maybe just one more thing. So we will have a special issue on astrobiology either this October, if the proofs are finished on time, or in November, with 2 papers on exactly the stuff that I've shown you in the last slides.
Yeah, thank you, Manuel, for a very interesting talk. I'm pretty sure there are some questions. I have many, so please raise your hand, whoever has. Yeah.
Thank you for the nice talk. I think I learned a lot. I'm not very familiar with all of this stuff, so I'm working on the high masters. I was wondering about this X-ray luminosity. At least for the high masters, we don't know where our X-rays are coming from, and I can imagine that for the sun, where this is also a non-LTE effect, the X-ray luminosity is hard to calculate. So I was wondering how this X-ray or XUV luminosity can be calculated for the sun, and how accurate is this?
Well, I think it could be more accurate. So most of it is based on observations of of stellar clusters, different ages, where they compare what's the short wavelength radiation that we can observe in the X-ray. And this is then basically scaled to other ages, and it's basically calculated via the Rossby number of the star and the turnover time of the convection within the star. But I think it's one of the weaknesses, because I think that it's not very well established. And in a study that we are currently performing, we are seeing that those values may diverge significantly if you, for instance, change the metallicity of the star. So it can change by orders of magnitude. So it would be nice to better constrain it, but still, you don't need a lot more X-ray flux actually, that you don't have stable atmospheres anymore. So the picture probably wouldn't change a lot if you constrain it better. And for TRAPPIST-1, as I said, we know from X-ray observations that the flux is about 100 times higher in the habitable zone than it is here on Earth at present. And that's far beyond any thermal stability limit.
Thank you for your talk. I have a question about the multiplicity of the star, because I guess you're only considering single star systems, but we know that solar type stars are expected to be 50% of binary. So do you expect this multiplicity to have an impact on your model and on the habitable zone?
Yes. Yes, I do. Sure. So, first of all, the occurrence rates of planets in the habitable zone around binary stars is lower than it is for single stars. So that's one effect. So I guess that it would become lower. Then there is also an issue. So there are diverging studies. Actually, some are saying that the interactions between the binaries probably increase the XUV flux. Others are saying the opposite. So this may also have an effect. It may also lead to higher eccentricities of the planets. So this may also have an effect on habitability. And all in all, I think that depending on the distance of the binaries or of the multiple stars, there may be habitable planets, but in general, it would decrease the number because many of those systems may not really provide habitable conditions for the planets.
Okay, thank you.
Hi.
Hi.
Thank you for your talk. This was really interesting. I have a question related to the fact that the composition of the disk also matters, of course, and there's been some thoughts about the fact that the presence of a giant outer gas giant, like a outer planet like Jupiter, depending on where it formed throughout the lifetime, might cause a very dry inner disk and therefore not very water-rich world. Is this something, like given the like how many giant planets we know there are, is this something that could be included as well, or what are your thoughts on that?
I think it's important. There are many factors coming into play. So first of all, if you take solar-like systems, I think there are estimates there is this review paper by Sean Ramian and Morbidelli, who state that about 1% of all systems may have a similar constellation with having Jupiter and probably a smaller gas giant outside. And so this probably really affects it on many different ways, because there are also the simulations that say that if you wouldn't have those gas giants, then probably Earth would have grown to a bigger size. As you said, that the water delivery would have been different. If probably Saturn was missing, then Jupiter would have migrated further inwards, probably destroying the inner solar system. So you may need some kind of that architecture, which probably would reduce the number, but I'm actually not so sure, because we have those rocky exoplanet occurrence rate, and somehow that's implicitly inside this thing. So if it probably would affect things like the water amount and stuff like that. And what's also interesting, there is this very famous 2000 book from Peter Ward and Donald Brownlee called The Rare Earth Hypothesis. And they say that you need Jupiter because it's shielding the Earth from asteroids and stuff like that. That's also probably wrong, because it can also, again, like the moon, have the other effect that it actually just draws in asteroids. So from that perspective, it doesn't really matter. But in general, I think you probably need some kind of that architecture.
Okay, thank you.
Thanks a lot for a great talk. So you, in the beginning of the talk, you mentioned a lot the toxicity levels potentially of large organisms that would live off this atmosphere. But could there be also conclusions drawn from organisms that wouldn't live off this atmosphere, but for example, marine life that would actually breathe an ocean, like from an ocean like this, how much of the dissolution of the atmosphere into the ocean, like would there be conclusions that we could draw also for marine life in this context?
That would be interesting to study. So the pH of the ocean changes, of course, if you increase the CO2. And I'm not entirely sure if I really understand by now how this would affect such complex life. Another question is, if you really have an ocean planet, or, well, you could, of course, have ocean life and also have continents, so that's not necessarily the case. So maybe some kind of complex life could evolve there also under different conditions, but I'm not entirely sure about that, I have to say. So I do not want to say any
Yeah.
stupid things.
As a side question also, would there be like, would we draw different conclusions with respect to the sterilization by supernova scenarios? Would then like an ocean protect the life forms that live inside?
To a certain extent, yes. And I have to say that a nearby supernova will most likely not sterilize the planet, because it's very hard to sterilize a planet, and the supernova must have to be somewhere within 0.3 parsecs, as recent studies show. But it will have a great effect on complex life, of course. So if you have complex land life, that will certainly be affected strongly. And it will also affect the ocean. So there are also theories that I think it was the end Ordovician mass extinction that probably was caused by a gamma ray burst relatively close to the Earth. And that also affected, well, at that point, you basically only had marine life, so it mostly affected marine life. And quite a large fraction actually died out. So it should also have an effect on ocean life, actually. Since most of the life, of course, is dependent on the upper part of the ocean, that brings in the energy, it also affects marine life to a certain extent.
Okay, thank you for the very nice talk. My question is, are you not concerned about anthropocentric selection effects? Because we need Jupiter, we need magnetic fields, we need liquid H2O. Are there not any other ways that life could exist that we simply don't think about at the moment?
Well, yes, I'm of course concerned about that. But you have to start somewhere. That's one thing, and the other thing is you have those certain limits, like the oxygen, for instance, that you will need if you want to form complex life. So you won't find any energy donor that can do that. You have fluorine, you have boron that basically, in theory, could bring you more energy. But if you really wanna, but they have other problems. They are very rare. But if you really wanna have some complex life, you certainly at least need oxygen, and that gives you some restrictions already. And the Jupiter thing, as I said, probably is not needed except for maybe other reasons, not for the asteroid thing. The magnetic field is likely also not needed or not that important, so we anyway do not include that. But of course, there could be other habitats, but they have some restrictions, of course. Like you don't, Titan-like habitats, you don't have the energy that you need. In marine habitats, if they have two big oceans, you won't be able to have the nutrient exchange with the planet, their interior, for instance. You may not even be able for life to originate. And I think it's a good starting point to start with Earth-like complex life, because we do not know what else would work. If something else would work, it would probably be very exotic, and with that probably also relatively rare. But of course, that doesn't concern microbial life. So that may be common, but in the end we do not know, because we do not know how the origin of life happened and how often it happens and under what conditions it happens.
Hey, I was just wondering, could you clarify what sort of assumptions you make around the planetary magnetic fields with these atmospheric retention models? Is there no field, or do you assume an Earth field, or?
We don't include the magnetic field. We are only concerned with thermal escape. So for that, it doesn't matter whether you have a magnetic field or not. So that's mostly important for non-thermal escape processes, like polar outflow, like interaction with the solar wind. And we do not include that. And magnetic fields are a tricky thing, because we actually do not know whether you need it or you don't need it for protecting your atmosphere. We do not know how often they may occur on planets, specifically on M dwarfs. That's why we, for the moment, do not account for them at all.
Okay, and I just had one more quick one. I saw on a slide you had listed a couple of specific elements, aluminium-26 and a couple of very heavies like thorium and stuff. Could you clarify the role that they play? Because Al-26 in particular, it's just a short-lived radioactive isotope. For me, it's not obvious why we would care about it.
So aluminum-26 was relatively important early on in the solar system, because the sun had quite an elevated aluminum, so the solar nebula, or the protosolar disk, had quite an elevated aluminum-26 value compared to the average galaxy. And that was important because it enabled the planetesimals to basically melt and to differentiate. And it was also important for volatilisation, so for losing some part of the water that you had. So you may need that you can indeed form habitable planets due to the differentiation process. And it was long thought that maybe around only 10% of stars in the galaxy may form with similar conditions than the Sun. But nowadays, well, it could also be that you actually need those big Wolf-Rayet stars, for instance, that produce aluminum-26, that you can collapse your stellar nebula to form protosolar disks. But it's certainly important to have elevated levels of aluminum-26 to have those differentiation processes. Then you have the radioactive elements like potassium-40, like uranium and thorium, that are important for the radioactive heat budget of your planet. If your radioactive heat budget is too high, you probably won't evolve something like plate tectonics because your crust will stay too sluggish, so too soft. If you have too little, you may just have a stagnant lid. And those elements evolve over galactic times because they are produced by supernovae, so their ratios in the galaxy change over time. So you have had much less of them early on, and you will have an increase in them over time. So probably there is some right window during galactic time where you can actually form habitable planets with the right radioactive heat budget. And the magnesium to silicon ratio also matters because if you have too much, if this ratio is too high, the geological behavior of your planet changes. And that may also affect degassing and other things like geologic activity, plate tectonics and stuff like that. But actually for that, and also the C2O ratio the same, but Kaustrup, I think, knows much more about that than I do.
Thanks.
Okay, is there any last question? Yeah, so if not, in general, I would like to understand what's your view on like big picture question, like are we alone? Because it seems like a grim view to me, but maybe it's my interpretation.
Well, in the universe, we are certainly not alone. I would be very surprised about that. In the galaxy, concerning life, I would also be surprised if we would be alone. Concerning intelligent life or even technological life, I wouldn't be surprised if we would be alone. Yeah. Because it's strongly dependent also on the lifetime of those technological civilizations, of course. But if you take just our numbers and assume some average 10,000 year lifetime, you basically come to something like unity. Yeah. So we could be alone in the galaxy on a technological basis. But I would be happy if we would find a planet with Earth-like atmospheres around stars like TRAPPIST or so, because then we would be wrong. That would be wonderful, because that's some scientific question that you could resolve, and it would also mean that complex life probably is much more common. So it would be nice to see something like that.
Okay, perfect. So thank you for a very interesting discussion session as well, and see you next time. So thank you.
Thanks.